Welcome everyone to today's Explainer. We are absolutely thrilled to have you here. Today, we're pulling back the curtain on the high-stakes, mostly invisible systems that literally run our physical world. I mean, think about it. The water you drink, the manufacturing plants producing our everyday goods, the massive infrastructure humming quietly in the background. What actually happens when the digital brains controlling all that physical muscle are left exposed? Well, today, we're diving deep into control systems cybersecurity, specifically focusing on the Horner OCS secure access architecture. It's a fascinating look at how modern industrial security actually works on the ground.
Look, if you take absolutely just one thing away from our time together, let it be this. Recent intrusions at U.S. water and wastewater utilities have made this terrifyingly clear. When an attacker manages to reach a PLC, a programmable logic controller, they aren't just poking around looking to steal corporate spreadsheets or financial data anymore. No way. They are reaching the physical process itself. Hackers are actively bypassing traditional IT perimeters to target real-world physical infrastructure.
Okay, let's dive into this. Here is our roadmap for understanding operational technology security today. 1. The physical cyber threat. 2. The remote access trap. 3. What secure by design actually means. 4. The Horner OCS solution. And 5. A defense-in-depth checklist.
Starting with Section 1, the physical cyber threat. Let's establish the downstream reality of a compromised PLC.
To really understand the solution, we first have to respect the problem, right? For plants running these controllers, cybersecurity simply cannot be treated as an IT afterthought. Actually, scratch that. It is a strict, absolutely critical operational requirement. Why? Well, just look at what sits downstream of controller access. We're talking massive industrial pumps, critical valves, delicate operational setpoints, and vital safety interlocks. If an attacker gains access to the PLC, they gain direct control of those physical components. A breach here doesn't just mean a crashed computer screen, it could mean a flooded facility or a damaged physical asset. It all starts with how that controller is architected.
Moving to Section 2, the remote access trap. Let's examine exactly how attackers manage to bypass traditional defenses.
And this brilliantly illustrates our core problem. If the stakes are really this high, how do they get in? Well, they often walk right through the doors we leave open for ourselves. It's the convenience trap. Facility operators set up port forwarding on routers, or they use shared VPN credentials with zero per-user accountability, or maybe they just install some random third-party remote tools. Each of these innocent-looking digital workarounds is a doorway. They act like modern-day Trojan horses, leaving difficult-to-manage paths where anyone with the right password or the right exploit can just slip right in. So, what does this all mean? It leaves us with a massive cliffhanger. I mean, the goal isn't to disconnect the facility entirely. Modern plants absolutely need remote visibility and remote support to run. So, the million-dollar question: how do we enable that required remote access without exposing the PLC directly to the public internet?
Section 3. What secure by design means. This is a fundamental shift in how we think about automation architectures.
Answering that cliffhanger requires us to move from reactionary to proactive security. True security comes from the very foundation of your setup. Secure by design means security is an inherent property of the system's architecture. It is not some feature bolted on afterward. It means really understanding your system, strictly limiting access, and maintaining a lifecycle defense, rather than just endlessly counting up vulnerabilities.
So the crucial point is this: less complexity is actually better. The number one is the goal. Control systems don't need more complexity to be secure. By reducing your surface, by consolidating down to just one platform and one software environment to inventory, you drastically reduce your attack surface.
Which brings us to Section 4. The Horner OCS solution. Let's look at a practical application of secure by design.
Let's break down this jargon for a second. An OCS, or Operator Control Station, combines PLC logic, HMI, routing, and I/O all into one single programmed unit through an environment called Cscape. As we just learned, consolidating all these functions into a single environment inherently acts as a major security control. Everything is configured in one toolchain, not spread across mismatched products.
Now, what's really interesting about this slide is the contrast. The traditional way essentially exposes a web server directly to the internet through forwarded ports. It's highly vulnerable.
On the flip side, the Horner OCS360 platform uses secure two-way ID checks, something called mTLS with X509 certificates. Both ends mathematically prove their identity before any data is exchanged, so no direct public PLC exposure, just secure, encrypted internal communication lanes. Of course, building this kind of defensible environment requires the right hardware, and automation distribution carries this full ecosystem. We're talking the XL7 and XL15 Prime all-in-one controllers, the embedded micro OCS controllers, and modular OCS I/O. Because visualization runs securely in the cloud, engineers get what they need without a forwarded port. This integrated lineup is exactly what a defensible automation environment requires.
Finally, Section 5, Defense in-Depth Checklist. Because, let's be real, no single controller or cloud service secures an entire facility on its own.
Protection has to be layered. Let's walk through the first half of this checklist. 1. Protect controller access with unique credentials. 2. Avoid direct internet exposure. 3. Use approved, secure remote access platforms. 4. And this is absolutely crucial, segment the automation network. You have to separate operational technology from standard business networks using industrial firewalls. Keep those office PCs off the controllers. And 5, reduce the attack surface by shutting down unused ports.
Let's move to the next slide and see how this builds into the vital maintenance side of things. 6. Maintain software and firmware. 7. Backup critical systems and keep a verified copy strictly offline. 8. Control system changes. 9. Monitor for warning signs. You've got to train your operators to spot unfamiliar screens or unexpected resets. And 10. Prepare an incident response plan so you know exactly who pulls the plug if the worst happens.
We'll leave you with this final provocative thought from our source material today. Control systems do not need more complexity to be secure. As you evaluate your own remote access setup, ask yourself, are you just layering on complex band-aids? Or are you building an architecture that's inherently easier to maintain? Ultimately, is your setup a secure fortress or a wide-open gate to your physical infrastructure? Thanks so much for joining us on this explainer. Stay curious and stay secure.